Okay. In the video which I was sent to you, in that all the calculations regarding the dimension of the specimen you have calculated. That is, I have shown how to calculate the diameter. The diameter is 18 mm. With a caliper you need to measure the diameter. Once you get the diameter of the given specimen, you need to find out the original cross-sectional area. To find out the cross-sectional area of a circular object is pi by 4 d square. Substitute the diameter which you have measured. The original cross-sectional area will get it as 254.47 mm square. This is the original gauge length. Original gauge length formula is 5 times the diameter. Whatever the diameter you are going to measure, you need to multiply that with 5. That will give you the original gauge length. In the sketch which I show, in this you are going to mark the gauge length in the specimen. For that you need to find out the gauge length, and from this point to up to this point, it is called as parallel length. Once you get the original gauge length, after that you need to measure the original parallel length. This reading I have taken it from your senior. The reading which you have given in the previous video, it was 192. In this case it is 160 mm. You can make those changes and you can calculate that. That is 160 mm. You need to measure the length, parallel length. This is called as parallel. From this point to this is the starting point and this is the end point. You need to measure this distance. That will give you the parallel length. After measuring the parallel length, this is before conducting the test. You need to do the observation. This is after conducting the test. You need to measure the final diameter. Means once the specimen breaks into two pieces, you need to measure the diameter of the specimen. If you see the specimen figure, this is original specimen, that is before loading, and this is after loading. In this you can see that the specimen has broken into two pieces. This is called as cup and this is cone. You need to join both the broken pieces. After that you need to measure the final diameter of the specimen. I have measured the final diameter, and the final diameter of the specimen is 10 mm. After that, once you get the final diameter, final cross-sectional area is, you have to use the same formula, pi by 4 d square. Substitute the diameter, final diameter, it is 10, it will be 78.54 mm square. After that, you need to measure the final gauge length. It is 114. Gauge length is nothing but, on this you are going to make the punch mark on the specimen. You need to measure that distance. In this we'll be making the punch mark on the specimen. In the video I have shown you how to make the punch mark. You need to measure that gauge length. That will give the final gauge length. As the member is subjected for tensile loading, the specimen will elongate. Means there will be increase in length. Here you can see that it is 114 mm, whereas the original gauge length is 90 mm. From 90 to there is an increase of 24 mm in the specimen. Similarly, you need to find out the final parallel length. Parallel length is the distance between these 2 points. This is the starting point and this is the end point. This is the specimen after failure. You need to measure the distance from here up to this point. That will give you the final parallel length. After measuring that, you will get it as 190 mm. These are the readings which has to be taken after the testing. Means after the specimen breaks into two pieces. Usually this tensile test is conducted to calculate the percentage of elongation in the specimen, percentage reduction in cross-sectional area. As the specimen elongates, there will be reduction in the cross-sectional area. You are going to find out the reduction in cross-sectional area. Similarly, you are going to find out the ultimate tensile stress, how much the maximum stress a specimen is going to take. That will give you the ultimate tensile stress. This is the breaking stress, the load at which the specimen breaks. From that you're going to get the breaking stress. The last one, you're going to find out the Young's modulus, that I will show while explaining the graph. You will see one by one. First one is percentage elongation. Elongation is nothing but, for example, if you take a strain, how you are going to measure the strain? Strain is nothing but change in length to original length. Here the change in length is final length minus original length divided by original length is L naught. It is denoted by L naught. Percentage elongation is nothing but strain measured in the specimen, change in length to original length. Substitute the final length of the specimen, original length of the specimen, similarly original length of the specimen. Substitute all the values. The final length of the specimen is 114, original length is 90. Here you have to take the gauge length, don't take the parallel length. Gauge length, it is 114 minus original, it is 5 times the diameter, 5 into 18 is 90, divided by original diameter, it is 90. Substitute all the values, you will get the percentage elongation as 26.67%. To convert this in terms of percentage, that's why I'm multiplying it with 100. This is how you are going to find out the percentage elongation. Similarly, as the member elongates in the longitudinal direction, there will be reduction in diameter. In the lateral section, you need to find out the reduction in the area. Okay, that is nothing but the member is subjected to strain. You have to use the same formula. That is original strain to the change in the strain to the original strain. How you are going to find out the change in the strain? Here you are finding percentage reduction in cross sectional area. Means to find out the change means first you have to know the original. Original will be same. Here the member is increasing his length, whereas the cross sectional area is reducing. Original cross sectional area will be more and the final cross sectional area will be less. Original minus final, that will give the change in cross sectional area divided by original cross sectional area. All these are calculated. Here you can see that the final cross sectional area and this is the original cross sectional area. Substitute these two values. Original cross sectional area is 254.34 and after the failure the cross sectional area is final cross sectional area is 78.5 divided by original cross sectional area, it is 254.34. Substitute that. To convert this into percentage, I am going to multiply it with 100. From this you will get the percentage reduction in cross sectional area is 69.13%. After that, ultimate tensile stress. Ultimate, as the name indicates, maximum. To find out the ultimate tensile stress, the formula which we will use to find out the stress is load divided by original cross sectional area. Here you are finding ultimate tensile stress, means you have to use the ultimate load taken by the specimen. For that, the formula is maximum load divided by original cross sectional area. Here you have to take original cross sectional area, don't take the final one. Here you have to take the original cross sectional area and you need to note down the maximum load from the reading. This is the these are the readings which you are going to take. That is during the conduction of the experiment. When you are going to conduct the experiment, when you apply the load, actually in this you need to make columns 1, 2, 3, 4 columns. First is applied load, it will be in kilonewton. Elongation, in this I have taken the average elongation in the extensometer. If you see the video, in that I have fitted 2 extensometer to the specimen. I have taken the average of that and this is the machine scale reading. Initially the deformation which are observed in the specimen which cannot be seen in the machine scale, these are in terms of that is, you can see that it is 2, that is 0.02, means which cannot be measured in machine scales. In machine scales you can measure 1 mm, 2 mm, 3 mm, like that machine scale reading is there. In that it is not possible to measure these values, that's why we have fitted extensometer to the specimen. That has to be noted down. And after that, stress and strain, actually here into 10 raised to minus 3 is that this should not be there. And strain doesn't have unit. Strain formula is change in length to, original change in length to original length. The unit of change in length is mm, and the unit of original length is also mm. Both will get cancelled and you will get it as, or strain doesn't have any unit. Stress unit is load divided by, stress is load divided by cross sectional area. Unit of load is Newton and area is mm square. Therefore stress unit is Newton per mm square. In this case, first you need to calculate the stress. Otherwise, first I will take down the maximum load. Here you have to see the maximum load which the specimen has taken, 70, 80, 90. This is 120. Okay. From here, you can see that this is the maximum load which a specimen has taken. Sorry, here 128 is there. In all the readings, the maximum load is 128. You have to substitute this load to calculate the ultimate tensile stress. 128 kilonewton in the formula. Ultimate tensile strength is equal to maximum load. It is 128 kilonewton. Here the unit should be in Newton per mm square. Kilo is nothing but 10 raised to 3. 128 into 10 raised to 3 divided by original cross sectional area is 254.34. Therefore, the ultimate tensile stress is 503.2 Newton per mm square. Now, this is the breaking stress. Breaking stress is nothing but stress is load divided by area. Breaking stress means the load at which the specimen breaks. From that, you are going to find out the breaking stress. Therefore, breaking stress is equal to breaking load divided by original cross sectional area. Here you have to substitute the breaking load, the load at which the specimen fails. Once again, you need to go to the tabular column. From that, you will get the load at which the specimen fails. Actually, after this 90, 80 is there. I think I have missed that. Here, you will get 80. Okay. At that particular point, the specimen has broken into 2 pieces. You have to take that 80. Okay. Therefore, consider that value 80. At that particular point, the specimen has broken into 2 pieces. Now, breaking load is 80 kilo 10 raised to 3 divided by original cross sectional area. Therefore, you will get it as 310.2 Newton per mm square. This is how the breaking stress is calculated. Now we'll see the tabular column. Here you are going to first find out the cross sectional stress in the specimen. Okay. For 10 kilonewton, when you apply 10 kilonewton, the elongation in the specimen is 0.02. From these two values, you need to find out the stress induced in the member and strain. As the member elongates, it will be subjected for strain as well as stress. You need to find out that. Okay. I will show you how to find out that stress. You know the formula. Stress is equal to load divided by area. Load is denoted by P divided by N. Oh, sorry, cross sectional area. You have to use it as A. Load divided by cross sectional area. In this, the applied load is 10 kilonewton. 10 into 10 raised to 3 into 10 raised to 3 divided by, you have to take original cross sectional area. Original cross sectional area is 254. 254 point something is there. I don't remember exactly the value. I think it might be 254.33. load divided by cross-sectional area, you will get the stress induced in the member as 0.0393 Newton per mm square. Similarly, you need to find out for 20 kilonewton load, how much is the stress induced. Just you have to change the load. Here you have to substitute as 20 into 10 raised to 3 divided by original cross-sectional area. You will get the stress induced. It has to be continued for all the readings. We need to find out all the stresses induced in the member. Now, I'm going to find out the strain induced in the specimen. Strain is nothing but change in length to original length. Strain is denoted by epsilon. Epsilon is equal to change in length. It is denoted by delta L or DL. Change in length to original length. You have to take the original length of the gauge length of the specimen. Change in length is 0.02 divided by the length of the specimen. If you calculate that value, you are going to get the change in length in the specimen. Change in length is 0.02 divided by the cross-sectional, original length. Original length is 90. 0.02 divided by 90 is the gauge length. From this, you will get it as 2.22 into 10 raised to minus 4. Similarly, you need to do the calculation for the second one. That is, the change in length is 0.03 divided by original length is 90. From that, you will get strain induced when you apply 20 kilonewton. Similarly, when you apply 30 kilonewton, the extensometer reading shows the elongation of the specimen is 0.05. 0.05 divided by 90 will give you the strain observed when you apply 30 kilonewton. Similarly, you need to continue until the last reading which you have taken in the tabular column. This is how you need to find out the stress and strain. This is after 90, 80 is there. You need to continue till then. Once you complete that, after that you need to draw stress versus strain. From that you are going to find out the Young's modulus in the specimen. The graph which you are seeing. Okay. In this, in the x-axis, it is strain. X-axis, you have to substitute the values or the strain which you have observed, and in the y-axis, you have to note down the stress observed in the specimen. Substitute the values, that is stress versus strain. Similarly, if you see the tabular column, when you apply 10 kilonewton, the observed stress is 0.0393. At 0.0393, the strain observed is 2.2 into 10 raised to minus 4. For each point, you need to draw the stress versus strain. In x-axis, you have to take down the strain, and in the y-axis, you have to take down the stress. After that, you have to plot the graph. This is how the graph which you are going to get. This is the point at which the specimen breaks into two pieces, and this is the maximum stress which a specimen is going to withstand. Actually, in this, we are not getting a proper upper and lower yield point. The seniors have not taken the reading properly. If you take the reading properly, you will get the upper as well as lower yield point. After that, for a particular point, the increase in the strain, it will be constant. The strain will increase, whereas the load will be constant. At a constant load, there will be increase in the or there will be deformation in the specimen. That will be noted as a parallel line, that is constant line. Why? Because once the material starts yielding, means it is going to change its state from elastic to plastic. Change of state takes place. For that reason, after that, the material is going to rearrange. For that reason, once again, it is going to regain its resistance power. At this particular point, completely the resistance will be lost. It will take some time to rearrange the molecules. Once that is done, you will get, once again, the material will take the load, and you will see the deformation. Or when once you're going to draw the stress versus strain plot, you will see like this. And this is the ultimate, and this is the proportional limit, where the stress will be directly proportional to strain. Up to this point, the Young's Hooke's law obeys. Hooke's law states that stress will be directly proportional to strain up to the elastic limit. This is the elastic limit. After that, you will see the plastic limit. Plastic is nothing but permanent deformation in the member. Elastic is after the unloading, the specimen is going to regain its original shape and size. When you load the specimen, there will be deformation in the specimen. After the removal of the load, the member is going to regain its original shape and size. Then the member can say that it is in elastic stage. Once it enters into the plastic stage, after the removal of the load, the member will not regain its original shape and size. Once you plot the stress versus strain, after that, you have to draw the slope A, B, C. From that, you will get the Young's modulus. Young's modulus is slope of stress by strain. Y-axis is stress, X-axis is strain. AB, you have to measure that. You will get it as 325.1 divided by strain. Strain observed, you have to note down that. From that, you will get the Young's modulus in the specimen. This is how the calculation is done. These are all the values which you have calculated. Okay. Now I'm going to ask you doubt. If you have any queries, you can ask. Or I will finish another 2 experiments calculation. After that, I will unmute and I will ask the questions. Now, this is the ISOD test. In the ISOD test, you can see that we have used the specimen. These are the dimensions of the specimen. In that, we are going to use V groove. V groove is used for ISOD test. You need to note down the observation, the total impact energy of the pendulum. The maximum impact energy of the pendulum is 164 joules for ISOD. And you need to find out the frictional loss. I shown you how to find out the frictional loss in the video. You can, if you still not able to recollect that, you can once again watch the video, and the clarifications can be done. This total permissible frictional loss is 0.5%. 0.5% of 164 joules, it is 0.82 joules. Observed frictional loss, it is 4 joules. Actually, the observed frictional loss is 2 joules. We observed 1 unit. Therefore, the observed is 2 joules. By mistake, I have written it as 4 here. Observed frictional loss is 2 joules. How to find out the correction factor? Correction factor is observed frictional loss minus permissible frictional loss. That is 4 minus 0.82. Actually, you have to take it as 2. Here I have taken it as 4. 4 minus 0.82, you will get it as 3.18. Now, once the pendulum or the hammer hits the specimen, there you are going to observe this energy absorbed by the specimen. It is 40 joules. Energy absorbed by the specimen, and at this point, the specimen breaks into 2 pieces. If the specimen doesn't breaks into 2 pieces, means it has undefined value. The energy obtained is 40 joules. I need to find out the total ISOD strength of the specimen, that is the toughness of the specimen. Energy absorbed by the specimen minus correction factor. 40 minus 3.182, it will be 36.82 joules. This is the isode impact strength of the specimen, that is 36.82 joules. This is how the isode calculation is done. The same procedure is used for Charpy also. Here the notch will change and the dimensions also changes. Here you are going to use U notch. These are the dimension. The depth is 2 mm. Sorry, the width is 2 and depth is 5. These are the observation. For isode, the maximum energy of the pendulum is 300 joules and the angle of fall, here it is 145 degree, whereas in this case it is 85 degree. If you see the mounting of the pendulum in the video, you will get to know the concepts clearly. Now you can see the total permissible frictional loss. It is 0.5%. 0.5% of 300. For the previous one also it is same. 0.5 into 300, it is 1.5 joules. The observed frictional loss. Without mounting the specimen, you need to observe the frictional loss in the impact testing equipment. You will observe it as 2 joules. Now the correction factor is observed frictional loss minus the permissible frictional loss. 2 minus 1.5, you will get it as 0.5 joules. Energy absorbed by the specimen. Once the specimen, the hammer or the striker hits the specimen, the energy absorbed by the specimen is 13 joules. The total Charpy strength of the specimen, that is, we have used mild steel for both the test. It is energy absorbed by the specimen minus the correction factor. Correction factor is 0.5. 13 minus 0.5. The needle was, or the dial was in between 12 and 14. That's why I have taken it as 13. 13 minus 0.5, it will be 12.5 joules. This is how the total energy absorbed by the specimen is calculated. Okay. The calculation part of Charpy as well as isode is over. Now I will stop the recording. If you have any doubts, you can ask.